Alright, so today I'm going to be explaining another important article in the field of geometric deep learning with the title on learning sets of symmetric elements. This paper in 2020. Learning from unordered sets is a fundamental learning setup, recently attracting increasing attention. For example, the popular article, Deep Sets. This article is the motivation of many researchers. So research in this area has focused on the case where elements of the set are represented by feature vectors, and far less emphasis has been given to the common case where set elements themselves adhere to their own symmetries. For example, if you have point clouds, some point clouds, and you can represent it in sets, and it doesn't matter the order of these sets. It could be the order of the sets, it could be anything, but at the end the feature representation is equivariant. It means that if you change the order of the permutation, it's like changing the order of your features. That is, we use it for computer vision to computationally make an object, make a 3D object. So in this paper, we present a principled approach to learning sets of general symmetric elements. We first characterize the space of linear layers that are equivariant both to element reordering and to inherent symmetries of elements, like translation in the case of images. We further show that networks that are composed of these layers, called deep sets for symmetric elements layers, are universal approximators of both invariant and equivariant functions. There is another paper called universal equivariance, so they unified all of these ideas into, and also they use the tensor notations, because you can also change from the order of tensor, either increasing or decreasing, when you pass through the layers of your equivariant layers, when you pass that. So you see the architecture of these deep symmetric DSS, deep sets for symmetric elements. We call it DSS. This is the architecture of DSS. So DSS layer, then after giving input to DSS layer, we have ReLU nonlinearity, then another DSS layer, then another ReLU, then DSS ReLU. But at the end, you need the sum pooling and fully connected for your prediction. But the key is that they are adding all of these. So they are adding all of these one with they have two kinds of layer, L1 and L2, but all of them, this block is called one layer. And you will see that there is a difference between L1 and L2. Of course, people have used this architecture in graph neural networks as well. In the case of, for example, instead of image, they have a subgraph of a graph, and instead of, for example, L1, they have instead of this convolutional layer L1, they have this just message passing on the subgraph for each of the subgraph, and then they align it together in here, that we add all of them here, and they align all of the subgraph together. But the idea is the same. That's why it's a universal function approximator. It's a universal approach to equivariance. So G-equivariant networks are a popular way to model G-equivariant functions. These networks are composed of several G-equivariant layers interleaved with activation layers like ReLU. So we interleave it with these ReLU nonlinearities. So linear layer, ReLU, linear layer, ReLU, and then finally fully connected and prediction. So characterizing linear G-equivariant layers can be reduced to the task of solving a set of linear equations in the following way. We are looking for a linear operator that commutes with all elements in G. So if you do group action on the X first and then linear layer is like doing linear layer then group action acting on that. But the key is this one. So for each entry, we have this formula, well, characterize that. And in fact, it's just identity plus B11 transpose. So we have two types of L1 and L2, but together they create the linear layer. So let's focus on that. First of all, we are in a products group. It's a symmetric group is defined by Sn, product of Sn and H. H is internal. I mean, each element, for example, each subgraph or each image, internally has equivariant properties. But even permuting among the images or among the subgraphs still holds. So that is another group. So that's why we multiply these things. So this is the core principle. If you think about this, because of this term, everything becomes symmetric. In fact, even the deep sets, they use plus to add the set elements. So that was, because when you add something, that's why you have symmetric function, the fully homogeneous symmetric function, symmetric polynomial. All of these things make it symmetric. I mean, in terms of permutation, because if you change the permutation, still your polynomial is the same. So the value is invariant. So what are these things? Which are trying to do some to create some invariance. Like in Riemannian geometry, we created the concept of curvature. We have positive, for example, for a cylinder, we have zero curvature. We have negative curvature. We have positive curvature, because we have created that Ricci curvature. I think it was something like this, first doing this gradient and then in order to make it, and you use tensors, for example, in all of the geometry, differential geometry of manifolds, to make it an invariant so that it, so making it invariant, it means that any geometry, it is invariant no matter what it is. Same for sets, any reordering of set elements is invariant, that number is not changed. So that's the motivation of all of these geometric deep learning. So the dimension of the space of G-equivariant linear function is just 1 over cardinality of your G and the summation over trace of P. The P is just permutation matrix corresponding to permutation G. And they have proved it here. So we have a linear subspace, which is a subspace of a space of all linear G-equivariant operators, but has the same dimension, which implies that both spaces are equal. And then a universal approximation theorem. This lemma says that there exists a polynomial function u such that for some elements L, which u of x is equal to u of y, if and only if x is h dot y for some h. And this theorem says that G invariant networks are universal approximators of continuous G invariant functions on K if H invariant networks are universal. So three possible types of equivariant functions can be considered. First, functions of the form this one, like assume that you have n elements, your set has n elements, but each one has d dimension, so it's like a vector, d by 1, d by 1. Each one is a vector. So you want to make sure that if you change the order of these elements, for example, the order is like this, if you just switch 3 and 1, it becomes 1, 3, the rest of them keep the same, then the results of your network will not change. There are huge examples in computer vision, in NLP, and anything you imagine, that this is a fundamental problem. I mean, research in this area is very fruitful in comparison to those pseudoscience in research on LLM, which is a pseudoscience. You cannot improve anything. But here, any innovation is an improvement for our understanding, because symmetry is inherent in nature. Even in DNA, you have T, C, A, G, A, T, C, G. So if you changed the order of one of them, then your children hair color is changed. So it's very fundamental for our living. Or in graph neural networks, they are fundamental. So there are many different kinds of symmetry. For example, in CNN literature, they only focus on rotation, translation, a little bit of reflection, and permutation. But permutation is very general, because you can use it for graphs as well. You can use it for 3D image construction as well. You can use it for molecular in chemistry as well. So permutation, that's why I love permutations. This permutation group, SN. And there are other theorems. For example, this one. But this figure shows that we consider all possible types of invariant and equivariant learning tasks. For example, classification, selection, merging, general equivariant tasks.